Hey everyone, and welcome to The Explainer. It is pretty wild to think about, but there are actually billions more connected devices on Earth right now than human beings. It's true. And today, we're going to demystify the incredibly complex, completely invisible blueprint that sits right beneath the surface of our modern lives. I'm talking, of course, about the Internet of Things. So, let's dive right into this. It's super easy to think of the Internet of Things as, I don't know, just kind of invisible magic, right? But it is actually a meticulously engineered system. Think about the urban grid tracking traffic and energy flow, automated factories running sophisticated robotics, or agricultural drones monitoring soil moisture from way up in the sky. These aren't just standalone, isolated gadgets anymore. They are all pumping massive, continuous data streams into one unified, globally connected architecture. Okay, so here's our roadmap for today. We'll be covering the evolution of connected devices, edge versus cloud computing, overcoming massive scaling bottlenecks, securing the network edge, the language of things, and finally, unifying the physical web. All right, let's kick things off with Section 1, Evolution of Connected Devices, from silos to the global web. So the timeline of connected devices really happens across three distinct eras. First up, we had machine-to-machine, or M2M. These were highly localized, closed-loop systems, literally cut off from the outside world. Then, of course, came the Internet of Things, which introduced massive IP-based architectures that finally connected these devices globally. And now? Well, now we're entering the Web of Things, or WOT. This takes all that raw hardware and actually integrates it right into the standard, everyday web interfaces we already use. The shift between these eras is pretty incredible when you map it out. M2M was completely boxed in, relying on dedicated physical links that severely bottlenecked any chance of growth. The IoT era came along and totally blew the doors off that box by tapping into the global internet backbone for dynamic connectivity. But the Web of Things? That transforms a raw, messy network into something genuinely elegant. By using uniform RESTful web standards, accessing a physical temperature sensor in a remote factory becomes exactly as easy and standardized as typing a website address into your browser. Which brings us to Section 2, Edge versus Cloud Computing, the Architectural Fix. There is a massive architectural conflict we have to talk about here. The cloud is absolutely fantastic for storing oceans of historical data and running heavy, complex analytics. But constantly transmitting all that raw data back and forth? It completely drains sensor batteries and chokes your bandwidth. Edge computing steps in to fix this by filtering and processing data locally, right at the source where it's gathered. In fact, experimental performance metrics show that edge computing drops packet loss down to a mere 1.6%. Compare that to the cloud's 4.8%. That isn't just a minor technical tweak, that is literally the difference between a system functioning perfectly and completely failing. And to put those numbers into perspective, let's look at a real-world scenario. Imagine an urban environment. If you've got smart parking meters or structural monitors on a bridge, a slight delay communicating with the cloud is perfectly fine. But what about an ambulance speeding toward an intersection? For emergency response systems coordinating traffic lights, we need mission-critical edge intelligence. A few seconds of latency or a 4.8% packet loss, completely unacceptable when human lives are on the line. That processing simply must happen at the edge, instantly. Moving right along to Section 3, Overcoming Massive Scaling Bottlenecks. Basically, what happens when scale breaks physics? We're currently facing three massive scaling bottlenecks. First, we literally ran out of IP addresses. When all of a sudden, your fridge, your watch, and your car all need their own unique web address, legacy IPv4 just doesn't cut it, which forced a mandatory, industry-wide shift to IPv6. Second, we have environmental constraints. Rural deployments, like smart farms, often have to survive on terribly low bandwidth. And third is the mobility problem. How on earth do you maintain a stable, persistent connection when a device, like a speeding commercial shipping truck, is rapidly crossing across different regional network boundaries? Because here's the reality. Legacy network architectures are literally cracking under the unprecedented weight of modern scale. If we try to shove billions of new devices through outdated IPv4 pipelines, or if we force heavy, cloud-centric models into low-bandwidth rural areas, the entire system fractures. We really have no choice but to completely transition our foundational architecture to prevent a total network collapse. Let's move to Section 4, Securing the Network Edge, or Protecting the Vulnerable. It really begs a serious question. I mean, a server sitting in a locked, climate-controlled, highly guarded data center is one thing, but what about a remote sensor sitting all by itself out in a farmer's field, or a tracking device attached to a logistics container traveling halfway across the globe? They are completely physically exposed. The answer the industry has arrived at is the fog computing shield. You've got dual threats out there: centralized digital cloud breaches and physical edge risks, like someone literally taking a crowbar to a piece of hardware. The solution is a layer defense. Fog computing sits right in the middle, between the edge and the cloud. It utilizes hierarchical layers and local authentication to neutralize those threats exactly where they happen. It acts as this hardened enclosure, meaning that if one local sensor gets compromised, it doesn't automatically hand over the master keys to your entire central network.
Section 5, the language of things, talking across silos. When you get down to it, it all relies on picking the right language. These little devices simply cannot use the heavy, data-rich protocols that run our modern desktop web browsers. Doing that would be like, well, hiring a massive 18-wheeler semi-truck just to deliver a single postcard. It demands way too much power and bandwidth. Instead, these resource-constrained environments require specialized, highly lightweight IoT messaging so they can actually survive on tiny batteries and spotty intermittent connections. You can kind of think of this as your protocol tool belt. If you're dealing with an incredibly unreliable industrial network, you'd use MQTT. It cleverly decouples the sender and receiver, so if the connection suddenly drops, your data isn't lost forever. If you have a battery-constrained sensor network, CoAP is your go-to for simple, lightweight requests. For localized home automation, you're looking at Zigbee, and for those massive scale deployments, think sensors spread across miles and miles of agricultural land, you deploy LPWAN. Using the wrong protocol in these scenarios is like trying to stream a 4K movie over a 90s dial-up modem. It just flat out won't work.
And finally, Section 6, unifying the physical web, the final blueprint. Transitioning from a bunch of fragmented hardware silos into a beautifully unified web takes 3 very specific steps. First, we model uniform interfaces using RESTful principles, treating physical functions exactly like everyday web resources. Second, we switch over to webhooks to handle data delivery way more efficiently. And third, we create what are called physical mashups. This is super cool. It just means blending data from entirely different physical devices, say a room thermometer and an automated window motor, into one seamless, interactive application. That webhooks mechanism I just mentioned, absolute game changer. Traditionally, networks rely on polling, where a server just constantly asks a device, hey, do you have new data? How about now? How about now? Literally exactly like a kid in the backseat asking, are we there yet? As you can imagine, that creates a massive amount of wasted bandwidth overhead. Webhooks flip the script. The device just sits quietly, doing its thing, until an event actually happens, and then it calls the server. This brilliant approach to data syndication saves incredible amounts of bandwidth, and it allows for the ultimate goal: a single web API that seamlessly blends a factory valve and a surveillance camera right into the same dashboard. So, when you bring all of this together, you get the final, unified blueprint. This is everything we've explored today working in perfect harmony. We've shifted over to low-latency edge processing. We've transitioned to continuous data streams. We've totally bypassed IPv4 limits for massive global scale. We've armored the whole thing using fog computing. And finally, we've deployed middleware to create this elegant, restful web of things. It really is just a stunning feat of modern engineering. The biggest takeaway for you today should be this: the Internet of Things isn't just some sci-fi future concept anymore. The architectural foundation is fully poured, it's dry, and it's functional right now. As this massive technology stack continues to make the physical and digital worlds completely indistinguishable, the power actually shifts over to you. The blueprint is ready and waiting. The real question is, what are you going to build with it? Thanks so much for joining me for this explainer, and keep exploring.